Hello, and a warm, gentle welcome. I'm so glad you're here, choosing to let the current of this story carry you toward the shores of sleep. Whether it's the deep stillness of night where you are, the soft glow of early morning, or that quiet, magical moment caught somewhere in between, I invite you to settle in. Before we begin our journey tonight, I find myself wondering, where in this wide world are you listening from? And what time does the clock show in your corner of the globe? If you feel so inclined, leave a little note in the comments. It's a quiet joy for me to imagine these stories drifting like dandelion seeds, finding soft places to land all around the planet. And while you're there, if this sonic stream helps you to unwind, to release the day, or even to find a moment of peace, please consider sharing a like or subscribing. It truly helps me to continue crafting these dreamy explorations for you. Tonight, our story is about water, the most ordinary and yet the most profoundly extraordinary substance in our universe. It is the river of time, the vessel of life, the mirror to our souls. We will follow its journey from the cold, silent depths of space, through primordial oceans and towering ice ages, across ancient myths and the foundations of empires, all the way to the simple, humble glass of water that might be resting beside you now. My only wish is that this story is just interesting enough to capture your imagination, but not so interesting that it keeps you from the rest you seek. The goal, after all, is to gently guide you into the deep, quiet waters of slumber. But if you do float along with me for a little while, you may just drift away, knowing why every sip you take is a taste of cosmic history, how ancient civilizations harnessed its power, and why the tears in your eyes and the oceans of our world share the same salty secret. So, find your coziest spot, let your body grow heavy, your breath slow and even, and let us begin. Long before our Earth was a swirling sphere of blue and white, before the first cloud cast a shadow upon its face, there was only the vast, silent theater of space. It was a place of profound emptiness, cold and dark, yet brimming with unseen potential. And in that great cosmic hush, a simple yet stubborn molecule began to form, two atoms of hydrogen, the universe's oldest and most abundant child, bonded with one atom of oxygen, an element forged in the heart of a dying star. This was H2O, water, born not on our world, but in the stellar nurseries and cosmic dust clouds scattered across the galaxy. The story begins with hydrogen. In the first few minutes after the Big Bang, as the universe expanded and cooled, hydrogen was already there, a boundless sea of single protons drifting through a fog of primordial energy. It is the universe's foundational element, the ultimate building block. From this simple starting point, everything else would eventually be built. Then came the stars, gravity, the universe's patient sculptor, began to gather these clouds of hydrogen into dense, spinning balls. In their cores, pressures and temperatures soared to unimaginable levels, igniting the fires of nuclear fusion. Here, in these stellar furnaces, hydrogen atoms were fused together to create helium, and then, in larger, more massive stars, heavier elements like carbon, nitrogen, and our crucial ingredient, oxygen. When these giant stars reached the end of their lives, they didn't simply fade away. They erupted in spectacular explosions known as supernovae, scattering their newly forged elements across the cosmos like a painter flinging vibrant colors onto a dark canvas. This stellar confetti, rich with oxygen, traveled for eons through the void. Now, picture these two elements, ancient hydrogen and stellar oxygen, meeting in the chilling expanse of interstellar space. It's not a bustling collision, more like a slow, deliberate dance in the near absolute zero temperature, on the surfaces of tiny grains of cosmic dust, often no larger than particles of smoke. These atoms found a place to meet and bond. Under the faint glow of distant starlight, they formed ice, tiny crystals of frozen water clinging to dust. This was the universe's first water, a delicate, cosmic frost. Over millions of years, this process continued. The dust grains, now coated in ice, became slightly stickier. They began to clump together, drawn by faint gravitational pulls. These icy aggregates grew, forming larger bodies, comets, which are essentially giant, dirty snowballs from the outer solar system, and asteroids, rocky bodies that can also contain significant amounts of ice in their interiors. This brings us to a beautiful and widely accepted theory about our own planet's water. Many scientists believe that Earth was born relatively dry. In its early, violent formation, it was a molten ball of rock, too hot to hold on to any water it might have formed with. So, where did our oceans come from? The answer, it seems, came from the sky, in an era known as the Late Heavy Bombardment. Roughly 4 billion years ago, the inner solar system was a cosmic shooting gallery, a relentless storm of comets and asteroids. Remnants from the formation of the planets rained down upon the young Earth. Each impact was catastrophic, but with the destruction came a gift. These celestial travelers, especially the icy comets, were delivering water, millions of gallons at a time. It was as if the universe, in its infinite wisdom, was patiently hydrating its newborn world, one cataclysmic splash at a time. While the image of a cosmic fire hose of comets is compelling, it's likely not the whole story. Another theory suggests that a significant portion of Earth's water came from within. As the molten planet began to cool and a crust formed, water trapped inside minerals deep within the Earth's mantle was released through volcanic activity. Volcanoes would have spewed immense clouds of steam and other gases into the primordial atmosphere, a process called outgassing. As the planet continued to cool, this vapor would have condensed and fallen as rain. In all likelihood, the truth is a combination of both, a delivery from the heavens and a generous offering from the earth itself. Some of our water is alien, and some is native, and here lies a thought to carry you into your dreams. The water molecule is incredibly resilient. It changes state from solid to liquid to gas. But the H2O molecule itself can survive for billions of years. This means that the very water in the glass beside you, the water that makes up over half your body, is composed of molecules that are older than the planet itself. They may have journeyed across the solar system on a comet, or been locked deep within the Earth's mantle for eons. They are silent witnesses to the birth of worlds. So, as you begin to drift, remember that you are, in the most literal sense, made of stardust and ancient rain. You are a vessel for water that has traveled through time and space to find its way to you. Picture the young Earth. It is not the tranquil blue marble we know today. It is a vision of chaos and fire, a seething, tormented world wrapped in a thick, toxic atmosphere. Its surface is a churning ocean of molten rock, constantly scarred by the impacts of celestial debris. Volcanoes, like wounds on the planet's skin, endlessly belch sulfurous gases and steam into a sky the color of rust. The crust, where it exists at all, is a fragile, shifting mosaic, cracking and reforming like thin ice on a boiling pond. It was a hellish landscape, yet it was here, in this inferno, that the stage was set for the arrival of the oceans. The transformation began with steam, as the planet slowly, painstakingly, began to radiate its primordial heat into space. It started to cool. The immense quantities of water vapor delivered by comets and released from the planet's interior that had saturated the atmosphere could no longer remain as a gas. They began to condense, forming clouds unlike any we have ever seen. They were planetary in scale, dense and dark, shrouding the entire globe and blocking out the faint light of the young sun. And then, it began to rain. This was not a gentle spring shower or a passing thunderstorm. This was a deluge of biblical proportions, a continuous, unrelenting rainfall that may have lasted for millions of years. Water hammered down upon the cooling rock, hissing and steaming as it hit the hot surface. It flowed across barren landscapes, carving the first tentative channels, gathering in volcanic craters and vast, low-lying basins. If you could have stood on the shores of this nascent world, you would have witnessed a planet being sculpted, softened, and born anew, drop by relentless drop. These first oceans were nothing like the cool, blue expanses we imagine. They were hot, perhaps close to boiling in some places. They were acidic, thanks to the dissolved carbon dioxide and sulfur compounds from the atmosphere. And they were in constant turmoil, stirred by furious geothermal activity. The planet's interior was still a furnace, and the ocean floor was riddled with underwater volcanoes and hydrothermal vents. These vents, like chimneys from the underworld, spewed out plumes of superheated, mineral-rich water, creating bizarre, alien landscapes beneath the waves. The water itself was thick with dissolved minerals, especially iron, which likely gave it a murky, greenish, or even reddish hue. Less a Caribbean paradise, more a primordial, steaming mineral soup. Yet, it was in this chaotic, chemical-rich broth that the oceans began their monumental work of shaping the planet. Water is a patient and powerful sculptor. Given enough time, it can move mountains. It seeped into the cracks of the cooling rock. When it froze in colder regions, it expanded, wedging the rock apart with immense force. It carried vast quantities of sediment-eroded rock and volcanic ash from one place to another, smoothing jagged peaks, filling in valleys, and etching out the first primitive riverbeds. In short, it began to give the Earth a geology, a personality. Water also played a crucial role in one of the most fundamental processes of our planet, the formation of continents. As the oceans spread, they cooled the thin crust, allowing it to thicken and stabilize in certain areas. These thicker, more buoyant sections of crust became the proto-continents, the seeds of the landmasses we know today. They slowly began to rise above the global ocean, like shy islands emerging from an endless bath. The circulation of water through the crust and mantle also helped to lubricate the slow, grand dance of plate tectonics, the process that drives continents to drift, collide, and break apart. All the while, water was not content to just sit on the surface. It was being integrated into the very fabric of the planet. It wormed its way into the crystal structure of rocks, was sucked into minerals, and was dragged deep into the Earth's mantle at subduction zones, where one tectonic plate slides beneath another, hidden from our view. Deep beneath our feet, there are vast quantities of water locked away. Some scientific models suggest that the Earth's mantle may hold several times more water than all the surface oceans combined. It is a hidden, subterranean ocean, not of liquid, but of water bound within the molecular matrix of superheated rock. Back at the surface, the sky was slowly beginning to change. The relentless, million-year rain had helped to scrub the atmosphere of its excess carbon dioxide, which dissolved into the ocean waters. As the atmosphere cleared and stabilized, sunlight could finally reach the surface with greater intensity. With that light came energy, the essential ingredient to set the stage for the most profound event in Earth's history, the emergence of life. The primordial oceans, once a symbol of chaos, had become a cradle. Their turbulent, mineral-rich waters provided the perfect laboratory for chemistry to become biology. They shielded the planet's surface from the harsh ultraviolet radiation of the sun. They moderated the planet's temperature. They took a barren, fiery sphere and transformed it into a water world, a shimmering blue jewel in the darkness of space, ready for whatever miracle was to come next. Life, as it turns out, is not a creature of comfort. It does not demand gentle breezes and sunlit meadows to begin. Instead, its first stirrings likely occurred in some of the most extreme environments on the young Earth. And for this delicate, improbable beginning, water was not just the stage, it was the script, the director, and the lead actor. Let us travel back in time, some 3.8 billion years, and dive deep into the hot, dark, primordial ocean. Here, miles below the surface, far from the sun's rays, the seafloor is a landscape of volcanic ridges. From cracks in the crust, known as hydrothermal vents, gush plumes of superheated water. This water, having circulated deep within the earth, is not pure HO. It is a chemical cocktail, rich in dissolved minerals like iron, sulfur, and magnesium, and gases like hydrogen sulfide. It is here, in the turbulent mixing zone, where this scalding, mineral-rich fluid meets the cold, deep ocean water, that many scientists believe the miracle of life began. This idea, known as the hydrothermal vent hypothesis, is compelling because these vents offer a trifecta of life-giving ingredients. First, there's energy. The steep temperature gradients and the chemical reactions between the vent fluid and seawater provide a continuous source of chemical energy, like a natural battery. Second, there are the raw materials. The water is a soup of simple organic molecules and the building blocks necessary to assemble more complex ones. Third, there's protection. The deep ocean shielded these nascent chemical reactions from the destructive ultraviolet radiation that bathed the planet's surface. Within the porous, honeycombed structures of these vents, tiny compartments could have acted as natural test tubes, concentrating chemicals and allowing complex molecules to form. It was here that simple molecules may have first linked together to form polymers, the chains that are the basis of life, like amino acids forming proteins, and water was the essential medium for all of it. Its famous ability as a universal solvent was critical. Water's polar nature allowed it to dissolve a vast array of salts, gases, and organic compounds, creating a dynamic environment where molecules could move freely, collide, and react. Without water to act as this molecular marketplace, the chemical steps toward life would have been impossibly slow, like trying to build a house with bricks that can't be moved. As these complex molecules formed, another of water's magical properties came into play. Water molecules have a love-hate relationship with oily, or hydrophobic, molecules. This relationship drives the formation of membranes. Imagine simple fatty molecules in the water. They naturally arrange themselves to minimize their contact with water, forming tiny, hollow spheres or bubbles. These were the first primitive cell membranes, delicate barriers that could enclose a small pocket of the primordial soup, creating a distinct inside and an outside. Once you have a container that can trap other molecules and replicate itself, you are no longer just dealing with chemistry. You are on the verge of biology. Inside every living thing today, from the smallest bacterium to the largest whale. This ancient watery legacy persists. Every cell in your body is essentially a tiny bag of water, where the intricate chemistry of life unfolds. Your blood, which carries oxygen and nutrients to every corner of your being, is mostly water. The tears that well in your eyes, the sweat that cools your skin, all are testaments to water's central role. Water doesn't just fill our cells. It gives shape and function to life's most important molecules. Take proteins, the workhorses of the cell. They are long chains of amino acids that must fold into incredibly precise three-dimensional shapes to function. This folding process is guided by water. Some parts of the protein are hydrophilic, water-loving, and are drawn to the watery environment, while other parts are hydrophobic, water-fearing, and tuck themselves away into the protein's core. The result is a beautifully complex and functional structure, like molecular origami, made possible only by the surrounding water. The same is true for DNA, the blueprint of life. The iconic double helix structure, that twisted ladder holding all our genetic information, is stabilized by the water molecules that surround it. The hydrogen bonds that hold the two strands together are stronger and more stable because of the properties of the aqueous environment. Even the process of DNA replication, the unzipping and copying of our genetic code, is a drama that plays out in a water-based solution. Once these first simple cells got their start, they began to change the world. Over billions of years, some evolved a revolutionary new trick: photosynthesis. Using the energy from sunlight, they learned to split water molecules, taking their hydrogen atoms and releasing the oxygen as a waste product. These early photosynthesizers, like cyanobacteria, began to pump this new, reactive gas into the oceans and atmosphere. This was the Great Oxidation Event, a profound transformation that turned the sky blue, created the ozone layer, and paved the way for more complex, oxygen-breathing life to evolve. It is a beautiful irony. Water, the cradle of life, was then broken apart by life to create the very air we breathe today. From the dark, hot depths of the ocean to the sunlit surface, and eventually, out onto the land, life's entire story is soaked in water. It is the solvent, the shaper, the protector, and the participant. Every beat of your heart, every thought in your mind, is powered by chemistry that happens in water. Life didn't just happen in water. Life is water, organized. It's easy for us to see the Earth as a static place. Continents sit where we expect them. Mountains stand tall and resolute, and oceans stay within their familiar borders. But this perception is an illusion born of our fleeting lifespan. The true history of our planet is one of constant, dramatic change, a story of floods, freezes, and colossal inland seas. And the primary artist of this relentless transformation has always been water. It is a force of immense power, reshaping the face of the Earth again and again with patience, unending work. Let's travel to a time of extreme cold, to the great ice ages. Our planet has not experienced just one. It has cycled through many periods of intense glaciation over hundreds of millions of years. These were not simply harsh winters. These were planetary deep freezes. Massive ice sheets, miles thick, crept down from the poles, grinding across continents and burying vast landscapes under their immense weight. The most dramatic of these episodes is known as Snowball Earth, a period around 700 million years ago, when it's believed that ice may have extended all the way to the equator. The oceans froze over. The land was entombed in glaciers, and the planet became a brilliant white sphere. reflecting sunlight back into space and making things even colder. It was a world locked in a crystal prison. How does such a planetary freeze even happen? Water itself is the key culprit. As global temperatures begin to drop, more snow falls and accumulates. Ice is highly reflective, a property known as albedo. It bounces sunlight back into space rather than absorbing it as heat. This creates a powerful feedback loop. More ice leads to more reflection, which leads to colder temperatures, which leads to even more ice. It's a runaway process that, once started, is incredibly difficult to stop. Yet, just as water helps to freeze the planet, it also holds the key to its thawing. Throughout these deep freezes, volcanic activity never ceased. Underneath the ice, volcanoes continued to erupt, venting carbon dioxide into the atmosphere, with no liquid oceans or plant life to absorb it. This CO2 began to build up over millions of years. Eventually, the concentration became so high that it created an intense greenhouse effect, trapping heat and causing the planet to warm rapidly. And then came the Great Melt. These thawing periods were not gentle spring awakenings. They were cataclysmic events. Glaciers melted at a staggering rate, unleashing unimaginable quantities of water across the land. Entire continents shed their icy coats, creating biblical floods that carved deep canyons and reshaped landscapes in mere years. A spectacular example of this glacial power is the formation of the Great Lakes in North America. During the last ice age, massive glaciers scraped and gouged the land, carving out deep basins. As the ice retreated about 14,000 years ago, the meltwater filled these depressions, creating the vast freshwater seas we know today. Every peaceful canoe ride on Lake Superior is a tribute to the memory of a 2-mile thick wall of grinding, moving ice. Glaciers also gave birth to enormous, temporary inland seas. At the end of the last ice age, a colossal body of water called Lake Agassiz covered a huge swath of North America, larger than all the modern Great Lakes combined. When the ice dams holding it back eventually broke, the resulting floods were among the largest the world has ever known, powerful enough to alter ocean currents and global climate. But water's artistry isn't limited to ice. Throughout Earth's history, sea levels have risen and fallen dramatically, flooding and exposing continents. During the Mesozoic era, the age of dinosaurs, a vast, shallow sea called the Western Interior Seaway split North America in two. You could have swum from modern-day Texas to the Arctic Ocean, sharing the warm waters with giant marine reptiles. These inland seas were not static. They ebbed and flowed with the planet's pulse, responding to tectonic shifts and changing climates. What was once a thriving marine ecosystem is now the high plains of Kansas, where fossils of fish and giant mosasaurs are found, silent proof of a drowned world. Even our deserts tell a story of a wetter past. The Sahara, now a symbol of aridness, was once a lush savanna dotted with lakes and rivers. As recently as 10,000 years ago, it supported thriving communities of humans and animals. Ancient rock art discovered in the heart of the desert depicts people swimming and animals like giraffes and crocodiles, ghostly echoes of a green Sahara. This constant reshaping of our world is a testament to water's dual nature. It is both a creator and a destroyer. It is an agent of erosion, the slow, steady force that wears down mountains. The Grand Canyon is a breathtaking monument to this power, carved over millions of years by the relentless work of the Colorado River, exposing layers of rock that read like a geologic diary. But water also builds. Rivers carry silt and deposit it to create fertile floodplains, the cradles of agriculture. Glaciers leave behind ridges of rock and soil called moraines that define the landscape. Ocean currents build beaches and deltas, creating new habitats for life. Today, water continues to transform our planet. But now, human activity has accelerated the pace. Melting glaciers are causing sea levels to rise. Climate change is intensifying storms and altering rainfall patterns. We have added our own, often chaotic, brushstrokes to the canvas. And yet, there is a profound comfort in knowing that water has seen it all before. It has frozen solid and boiled into steam. It has flooded continents and carved canyons. It has survived asteroid impacts and mass extinctions. Through every transformation, it persists, flowing, shaping, and surprising us. It reminds us that our world is not fixed or permanent, but fluid and ever-changing, and in that fluidity lies its enduring, restless beauty. For billions of years, water had shaped the planet. It carved canyons, filled oceans, and set the stage for life itself. Then, a new kind of creature appeared on the scene, a creature that walked upright, fashioned tools from stone, and gazed at the stars with a dawning curiosity. Most importantly, this creature got thirsty, and with that simple, primal need, a new chapter in water's long story began, a chapter where it became not just a force of nature, but a partner, a deity, a source of conflict, and the lifeblood of civilization. This is the story of water and us. From our very earliest origins, water was our guide. Early hominins, our distant ancestors, did not choose their homes randomly. They were drawn to water like moths to a flame. Rivers, lakes, and springs were the centers of their world. In the sun-scorched savannas of Africa where humanity first arose, a water hole was more than just a place to drink. It was a community hub, an oasis of life where predators and prey, including our own ancestors, came together in a fragile truce dictated by thirst. Proximity to water meant survival. It provided drinking water, of course, but also a reliable source of food, fish, edible plants, and the animals that were drawn to drink. As humans evolved and became more mobile, they migrated out of Africa and across the globe, and their pathways were etched by water. They followed coastlines, where marine resources were plentiful, and traced the courses of great rivers deep into new continents. The Nile, the Tigris and Euphrates, the Indus, the Yellow River. These were not just geographical features, they were the arteries of human expansion, the liquid highways that carried humanity to every corner of the earth. It was on the banks of these rivers that humans decided to stop wandering and build. The first villages, towns, and cities almost invariably grew up around a reliable source of fresh water. The annual, predictable flooding of rivers like the Nile deposited rich, fertile silt, making agriculture possible. This agricultural revolution was a watershed moment. For the first time, humans could produce a surplus of food. This freed people from the constant struggle of hunting and gathering, allowing them to specialize in other tasks: building, crafting, governing, and thinking. Civilization, in all its complexity, began to bloom in the fertile mud of riverbanks. As societies grew, water became more than a resource. It became sacred. In nearly every ancient culture, water was imbued with divine power. In Mesopotamia, where unpredictable and violent floods could wipe out entire cities, water was a fearsome and respected deity. In Egypt, the gentle, life-giving rhythm of the Nile's flood was seen as a gift from benevolent gods, and it shaped their entire worldview, their calendar, and their religion. In the Indus Valley, cities like Mohenjo-daro were built with astonishingly sophisticated water management systems. including the Great Bath, a large public pool that was likely used for ritual purification. A testament to water's spiritual significance, water was woven into the fabric of mythology, often seen as the primordial substance from which all of creation emerged. The book of Genesis begins with darkness over the surface of the deep. Hindu cosmology imagines the world resting on a cosmic ocean. For the ancient Greeks, the river Oceanus encircled the world. This recurring theme speaks to a deep, intuitive human understanding. Before there was anything else, there was water, vast, silent, and full of potential. But this divine entity had a dual nature. Water gives life, and it takes it away. Floods could be nourishing, but they could also be catastrophic. Droughts could wither crops and bring famine. The Epic of Gilgamesh, one of humanity's oldest literary works, features a great flood story, a narrative that echoes in cultures across the world. It's a timeless reminder of humanity's precarious relationship with the forces of nature. To survive and thrive, humans had to get clever. They began to manage water. They dug wells to tap into hidden groundwater. They built canals and irrigation systems to divert river water to their fields, turning arid land into productive farmland. They constructed reservoirs to store water for dry seasons. In Mesopotamia and Egypt, these feats of engineering led to agricultural surpluses that fueled the growth of powerful empires. Water management became a form of power. The king or pharaoh, who could control the water, who could organize the construction of canals and predict the floods, was seen as having a divine mandate to rule. As cities swelled, so did their water needs. A city cannot function without a reliable supply of fresh water and a way to remove waste. This led to some of the earliest and most impressive feats of urban engineering. The Minoans on Crete built terracotta pipes and aqueducts. The Romans would later perfect this art. But even in the ancient Indus Valley, cities had covered sewers and private bathrooms with drainage systems. Where there was good water management, there was health, order, and prosperity. Where there was not, cities withered and died. Water also became the great connector of the ancient world. Rivers and seas were the first superhighways. Boats carried goods, people, and ideas across vast distances, weaving a network of trade and cultural exchange. The Mediterranean Sea became a bustling hub, linking the civilizations of Greece, Rome, Egypt, and Phoenicia. Water, the substance that had once defined the boundaries of human settlement, now became the medium that broke those boundaries down. In every aspect of early human life, from daily survival to the rise of empires, from spiritual beliefs to the spread of ideas, water was the common thread. We followed it, we worshipped it, we feared it, and we learned to harness it. We built our world upon its banks, and in doing so, we tied our destiny to its eternal, flowing current. As human societies grew more complex, our relationship with water evolved from one of reverence and reliance to one of ambitious control. We were no longer content to simply live beside the water. We wanted to command it, to move it across vast distances, to store it, celebrate it, and build our grandest monuments around it. This was the age of engineering, where humanity's ingenuity was put to the test against the fundamental challenge of getting water where we wanted it to go. Let's start with the simple, yet profound, innovation of the well. A well is more than just a hole in the ground. It is a gateway to a hidden world. The discovery that fresh, clean water could be accessed by digging deep into the earth was revolutionary. Some of the oldest known wells date back over 8,000 years, freeing communities from their dependence on surface water. which was often seasonal or contaminated. A well meant security. It meant a permanent settlement could thrive even far from a river. In the arid landscapes of ancient Persia, this concept was taken to an astonishing new level with the creation of the connet. A connet is a masterpiece of subterranean engineering, a gently sloping underground tunnel that taps into an aquifer at the base of a mountain and carries the water 4 miles across the desert to a village or farm. These systems were built by hand, with vertical shafts dug every 100 feet or so for ventilation and maintenance. They delivered cool, clean water with zero evaporation, allowing cities to blossom in some of the harshest environments on Earth. It was humanity's first great plumbing system, silent and invisible beneath the sand. In India, another architectural marvel emerged, the stepwell. More than just functional water sources, stepwells were inverted temples, works of art carved deep into the earth. Intricate, symmetrical staircases descended stories down to the water level, allowing access year-round as the water table rose and fell with the monsoons. They were cool, shaded sanctuaries from the searing heat, adorned with beautiful carvings and galleries. They were community centers, places for gathering, socializing, and religious rituals. They represent a beautiful fusion of engineering, art, and spirituality, a celebration of water in its purest form. But when we think of ancient water engineering, one civilization stands above all others: Rome. The Romans were the undisputed masters of moving water. Their aqueducts are one of the most enduring symbols of their power and ingenuity. These were not simply channels. They were monumental structures of stone and concrete, marching across the landscape on soaring arches, carrying a constant stream of fresh water from distant mountain springs to the heart of their bustling cities. The aqueduct of Segovia in Spain and the Pont du Gard in France still stand today, silent testaments to the precision and ambition of Roman engineers. They understood gravity, gradients, and fluid dynamics with a sophistication that would not be surpassed for 1,000 years. And where did all this water go? Once it reached the city, it was distributed through a complex network of lead and terracotta pipes to public fountains, wealthy homes, and, most famously, the public baths. The Roman baths, or thermae, were the heart of Roman social life. They were far more than just places to get clean. They were vast, opulent complexes that housed hot and cold pools, steam rooms, exercise yards, libraries, and even snack bars. They were the social hubs of the city, where people from all classes could meet, relax, and conduct business. The constant flow of fresh water from the aqueducts kept them clean and hygienic. They were a public good, a symbol of the empire's commitment to the health and well-being of its citizens. But Roman ingenuity wasn't just about bringing water in. It was also about getting it out. They engineered one of the world's earliest and most effective sewer systems, the Cloaca Maxima in Rome. This greatest sewer was a massive underground channel that drained waste from the city and carried it to the Tiber River. This fusion of water supply and sanitation was a hallmark of a truly advanced urban society. While the Romans perfected the art, they were not alone. The ancient Greeks built sophisticated cisterns and fountains. In the Americas, the Inca were masters of mountain hydraulics, engineering stone channels and terrace farms that precisely channeled water from glacial streams down steep mountainsides. In the deserts of modern-day Jordan, the Nabateans carved the city of Petra out of solid rock. They were masters of water harvesting, chiseling channels into the cliffs to capture precious flash flood water and direct it into vast underground systems. Their city thrived in a place where survival should have been impossible. All thanks to their mastery of liquid logistics. These great works of engineering were more than just practical. They were statements of power and permanence. The ability to control water was the ability to control life itself. A king who could build a reservoir that saved his people from drought, or an aqueduct that made a city flourish, was seen as a powerful and legitimate ruler. And for the people, these systems created a sense of civic pride and shared identity. The public fountain was the neighborhood meeting place. The bathhouse was the center of social life. Water infrastructure brought people together, physically and socially, in a shared reliance on this precious, managed resource. Even today, we live in the legacy of these ancient engineers. Beneath our modern cities lies a vast, invisible network of pipes, pumps, and treatment plants, a system far more complex, but built on the same fundamental principles pioneered thousands of years ago. Every time we turn on a tap, we are participating in a tradition of engineering that stretches back to the first person who decided that the water shouldn't just be where nature left it, but where we needed it to be. For most of human history, the concept of clean water was simple. If it looked clear and didn't taste bad, it was probably fine to drink. This was a gamble, a daily game of chance with an invisible enemy. Beneath the crystal clear surface of a babbling brook or a village well, a microscopic world of danger could be lurking. Bacteria, viruses, and parasites responsible for devastating diseases. This is the story of humanity's slow, often painful, awakening to the world of germs and our epic quest for truly safe water. For millennia, people had an intuitive, if incomplete, understanding of water quality. Ancient texts from India, dating back nearly 4,000 years, describe methods for purify water, including boiling it over a fire, filtering it through sand and charcoal, and exposing it to sunlight. The ancient Egyptians used the chemical alum to cause suspended particles to clump together and settle, a process called coagulation that is still a cornerstone of modern water treatment. These were remarkably effective methods, born of careful observation, even without any knowledge of the microscopic culprits. But as cities grew larger and more crowded, these traditional methods were overwhelmed. Medieval European cities became a case study in what happens when a large population lives without proper sanitation. Rivers that flowed through cities like London and Paris became open sewers. They were dumping grounds for human waste, animal carcasses, and the refuse from tanneries and butcher shops. The River Thames in London was famously described as being thick enough to walk on in some places. People knew the water was foul, but they didn't fully understand how dangerous it was. Faced with undrinkable river water, many people turned to a safer, if more intoxicating, alternative, beer and wine. The brewing process, which involved boiling the water, killed most pathogens. For centuries, ale and small beer, a weak, low-alcohol version, were the beverages of choice for everyone, including children. Not for the birds, but for basic hydration. Water was for washing and for carrying waste away, but not for drinking. This reliance on alcohol couldn't prevent the inevitable public health crisis. By the 19th century, the Industrial Revolution had triggered an explosion in urban populations. Cities like London were dangerously overcrowded and spectacularly unsanitary. The result was catastrophic outbreaks of waterborne diseases, especially cholera. For a long time, the prevailing scientific theory for how diseases spread was the miasma theory, the belief that diseases were caused by bad air or foul smells. When cholera struck, people would burn incense and hold perfumed handkerchiefs to their noses, believing they were fighting the disease. all while continuing to drink from the contaminated water source that was the true killer. The turning point came in 1854, during a terrifying cholera outbreak in the Soho district of London. A physician named John Snow, a skeptic of the miasma theory, did something revolutionary. He went door to door, interviewing residents and marking the location of each cholera death on a map. His map revealed a chilling pattern. The deaths were clustered around a single public water pump on Broad Street. Snow presented his findings to the local authorities and convinced them to take the handle off the pump. Almost immediately, the outbreak subsided. John Snow's work was a landmark moment in the history of public health and epidemiology. It was the first compelling evidence that cholera was not in the air, but in the water. This discovery, coupled with Louis Pasteur's germ theory of disease a few years later, sparked a sanitation revolution. Cities began to invest massively in new infrastructure. In London, an engineer named Joseph Bazalgette designed and built a vast, interconnected sewer system that is still in use today. It intercepted the city's waste before it could reach the Thames and carried it miles downstream to be released into the sea. At the same time, new methods of water treatment were being developed. Slow sand filtration was found to be incredibly effective at removing particles and microbes. Then, in the early 20th century, came the single most important breakthrough in the history of safe drinking water: chlorination. Scientists discovered that adding a tiny, carefully controlled amount of chlorine to water could kill off most harmful bacteria and viruses. It was cheap, effective, and could be implemented on a massive scale. Within decades, cities across the developed world adopted chlorination, and the rates of diseases like cholera and typhoid plummeted. The idea of turning on a tap and drinking the water without fear, once an unimaginable luxury, became a normal part of daily life for millions. This victory, however, is not yet universal. Even today, billions of people around the world lack access to safely managed drinking water. Waterborne diseases remain a leading cause of illness and death, especially for young children. But the quest continues. New technologies, from advanced membrane filtration and UV sterilization to simple, low-cost household filters, are bringing safer water to more communities every year. The journey from the contaminated rivers of the past to the clean water in your glass is a story of scientific discovery, engineering marvels, and a fundamental shift in our understanding of the world. It's a quiet triumph we celebrate with every safe, refreshing sip. Water seems so simple. It is clear, odorless, and tasteless, but this apparent simplicity hides a world of bizarre and wonderful properties. If you could shrink down to the molecular level, you would see that water is not a placid substance at all. It is a dynamic, energetic world of pushing, pulling, and sticking together that makes life as we know it possible. The secret to water's magic lies in its shape. A single water molecule, H2O, is made of one oxygen atom bonded to two hydrogen atoms. But these atoms are not arranged in a straight line. They form a bent V shape, like a tiny boomerang. This bent shape creates what is called a polar molecule. The larger oxygen atom pulls the shared electrons closer to it, giving it a slight negative charge, while the two hydrogen atoms are left with a slight positive charge. This makes a water molecule like a tiny magnet, with a positive and a negative pole. This polarity is the source of almost all of water's superpowers, because they are like little magnets. Water molecules are incredibly attracted to each other. The positive hydrogen end of one molecule forms a weak bond with the negative oxygen end of another. This is called a hydrogen bond, while a single hydrogen bond is weak. A vast network of them creates a powerful collective force. This stickiness between water molecules is called cohesion. You can see it in action every day. It's what allows water to form beads on a waxy leaf, or to create that beautiful, rounded dome on top of a full glass of water. This cohesion creates a phenomenon called surface tension. At the surface of the water, the molecules are pulled more strongly inwards by the molecules below them, creating a kind of invisible, elastic skin. This skin is strong enough to support small insects like water striders, allowing them to seemingly walk on water. Water molecules don't just stick to each other. They also stick to other things. This property is called adhesion. Together, cohesion and adhesion create a miraculous effect called capillary action. In a narrow tube, like the stem of a plant, water will actually climb upwards, defying gravity. The water molecules adhere to the sides of the tube and cohere to each other, pulling the whole column of water up. This is how a giant redwood tree can pull water from its roots hundreds of feet up to its highest leaves. Another of water's superpowers is its incredible ability to store heat. It has a very high specific heat capacity, which means it takes a lot of energy to raise its temperature by just 1 degree. This property is crucial for regulating the Earth's climate. Our oceans are like giant thermal batteries. They absorb huge amounts of heat from the sun during the day and in the summer, and then release it slowly at night and in the winter. This moderates global temperatures, preventing extreme swings and making the planet more habitable. This is also why coastal areas tend to have milder climates than inland regions. But perhaps water's most famous and most life-giving property is its role as the universal solvent. Because of its polarity, water is exceptionally good at dissolving other substances. When you put salt in water, for example, the positive and negative ends of the water molecules surround the sodium and chloride ions of the salt, pulling them apart and holding them in the solution. This is how nutrients are transported in our blood, how rivers carry minerals to the sea, and how a cup of tea gets its flavor from the leaves. Finally, let's consider water's strangest party trick. Almost every substance on Earth becomes denser when it freezes, but water does the opposite. When water freezes, its molecules arrange themselves into a rigid, open, crystalline lattice. This structure takes up more space than the jumbled arrangement of molecules in liquid water. Because it takes up more space, it is less dense, and that is why ice floats. This simple fact is profoundly important for life on Earth. If ice were denser than water, lakes and oceans would freeze from the bottom up in winter, entombing all aquatic life in a solid block of ice. Instead, the floating layer of ice acts as an insulator, protecting the liquid water and the life within it from the freezing air above. The simple, humble water molecule is a chemical masterpiece. Its bent shape gives rise to a cascade of unique properties that sculpt our planet, regulate our climate, and make every living thing tick. It is a substance of quiet miracles, a testament to how the simplest things in the universe are often the most profound. Water is never still, even in the calmest lake or the deepest ocean. It is in constant motion, but this movement is not random. It is part of a grand, planetary-scale performance known as the hydrological cycle, or the water cycle. This is the endless dance of water, a continuous journey from ocean to sky, from sky to land, and from land back to the ocean again. It is a cycle powered by the sun, driven by gravity, and it connects every living thing on Earth. Let's begin our journey in the vast, sunlit expanse of the ocean, which holds over 97% of all the water on our planet. As the sun's rays warm the surface, they give energy to the water molecules, Some gain enough energy to break free from the liquid and rise into the atmosphere as an invisible gas, water vapor. This process is called evaporation. Every day, the sun lifts trillions of tons of water into the sky in this silent, gentle process. It's the largest solar-powered engine in the universe. But evaporation doesn't only happen from oceans. It happens from lakes, rivers, and even from a small puddle on the pavement after a rain shower. Plants also play a crucial role. They draw water up from the soil through their roots and then release water vapor into the air through tiny pores in their leaves. This is called transpiration. Together, evaporation and transpiration send a constant stream of moisture into the atmosphere. As this warm, moist air rises, it begins to cool. Cool air cannot hold as much water vapor as warm air. So, the water vapor begins to condense back into tiny liquid water droplets. These droplets are so small and light that they can float in the air. They gather around microscopic particles of dust, salt, or pollen, and as millions of them come together, they form a cloud. Clouds are the visible manifestation of water's journey into the sky. They are floating reservoirs, carrying vast amounts of water across the globe, driven by the winds. As more and more water vapor condenses, the droplets in the cloud grow larger and heavier. Eventually, they become too heavy to stay suspended in the air. Gravity takes over, and they fall back to Earth as precipitation. This can take many forms depending on the temperature: gentle rain, fluffy snow, tiny pellets of sleet, or hard balls of hail. Once the water reaches the ground, its journey can take many different paths. Some of it might land on a mountainside as snow, where it can remain frozen for months or even centuries as part of a glacier. This acts as a natural frozen reservoir, slowly releasing water during the warmer months. Some of the water will flow over the surface of the land as runoff, collecting in streams and rivers, always moving downhill, pulled by gravity, on its way back to the ocean. Along the way, it erodes the land, carrying sediments and shaping the landscape. But a significant portion of the water soaks into the ground. This process is called infiltration. The water seeps down through the soil and rock, replenishing underground reservoirs called aquifers. This groundwater can stay underground for days, years, or even millennia. It moves very slowly, but it eventually emerges back at the surface in springs, or seeps into rivers and lakes, providing a steady supply of water even during dry periods. This endless cycle is not a simple, closed loop. It is a complex web of interconnected pathways. A single water molecule might evaporate from the Pacific Ocean, travel in a cloud over North America, fall as snow in the Rocky Mountains, melt in the spring and flow down the Colorado River, be used to irrigate a farm in Arizona, be taken up by a lettuce plant, be eaten by a person, and then be released back into the atmosphere through their breath. The journey is continuous and infinitely varied. The water cycle is also Earth's natural purification system. When water evaporates, it leaves behind salts, minerals, and other impurities. The water vapor that rises is essentially pure H2O. This is why rainwater is naturally fresh. However, as it falls through the atmosphere, it can pick up pollutants from the air, which is how acid rain is formed. The water cycle is the heartbeat of our planet. It dictates our weather, shapes our landscapes, and sustains all life. But this ancient, elegant cycle is now being disrupted by human activity. Climate change is intensifying the cycle. Warmer temperatures mean more evaporation, which can lead to more severe droughts in some regions. A warmer atmosphere can also hold more moisture, which means that, when it does rain, it can rain much more heavily, leading to more extreme floods. We are turning up the volume on the planet's water cycle, making it more volatile and less predictable. Understanding this endless dance is crucial. It reminds us that all water is connected. The water we use in our homes, on our farms, and in our industries is not a new resource. It is borrowed from this ancient cycle, and every drop we use, and every pollutant we add, will eventually find its way back into the system, affecting someone or something downstream. It is a shared resource, a shared responsibility, and a shared destiny, all flowing in one continuous, eternal stream. There is a quiet magic in turning on a tap and having clean, safe water flow out instantly. It is a convenience so deeply woven into the fabric of modern life that we rarely pause to consider the immense, invisible system that makes it possible. The journey of water from a distant river or a deep underground aquifer to your glass is a triumph of engineering, chemistry, and public health. It is a story of a carefully managed, multi-step process designed to transform raw nature into a product that is safe, reliable, and life-sustaining. Let's trace that journey. It begins at the source. Most of our tap water comes from either surface water rivers, lakes, and reservoirs, or groundwater, which is pumped from underground aquifers. These sources are carefully chosen and protected, but the raw water they contain is far from pure. It can contain sediment, algae, bacteria, and a whole host of other microscopic contaminants. The first step is to get this water to a treatment plant. Large intake pipes, often located deep in a reservoir or river, draw the water in, passing it through large screens to filter out debris like leaves, sticks, and the occasional lost fish. Once at the treatment plant, the real purification begins. The first major stage is coagulation and flocculation. It sounds complicated, but the idea is simple. Chemicals called coagulants, like alum, are added to the water. These chemicals have a positive charge that neutralizes the negative charge of dirt and other dissolved particles in the water. This causes the particles to stick together, forming larger, heavier particles called floc. The water is then gently stirred in large basins to encourage more of these particles to clump together. Next comes sedimentation. The water, now full of heavy floc, is moved to large, quiet tanks called sedimentation basins. Here, the water sits for several hours, and gravity does its work. The heavy floc particles slowly settle to the bottom, forming a layer of sludge, which is later removed. The clearer water from the top then moves on to the next stage. This stage is filtration. The water is passed through layers of sand, gravel, and charcoal. This process removes even smaller particles that didn't settle out, including dust, parasites, bacteria, and viruses. Think of it as a much more sophisticated version of the natural filtration that happens when water seeps through the ground. The water that emerges from the filters is remarkably clear, but it's not quite ready to drink yet. The final, crucial step is disinfection, to kill any remaining microorganisms and to keep the water safe as it travels through the pipes to your home. A disinfectant is added. Most commonly, this is chlorine. A small, carefully controlled amount of chlorine is incredibly effective at killing harmful germs. Some cities also use other methods like ozone or ultraviolet UV light to disinfect the water. Many communities also add fluoride to the water at this stage. Fluoride is a mineral that has been proven to strengthen tooth enamel and prevent cavities, and its addition to public water supplies is considered one of the great public health achievements of the 20th century. Now, The treated water is ready for its final journey. It is pumped into a vast, hidden network of pipes that lies beneath our streets. This distribution system is like the circulatory system of a city. It includes massive water mains, smaller pipes that branch off to neighborhoods and individual houses, as well as pumps to maintain pressure and large storage tanks or water towers to ensure a steady supply, especially during times of high demand, like early mornings when everyone is taking a shower. Maintaining this underground network is a constant challenge. Engineers monitor water quality and pressure, and crews are always on standby to repair leaks and breaks in the aging pipes. And then, finally, after this long and complex journey, the water arrives at your home. You turn a handle, and it flows, clear and cool, into your glass, the end of one journey, and the beginning of another, as it becomes a part of you. But the story doesn't end there. After you use it for drinking, cooking, or washing, the water flows down the drain and enters another network of pipes, the sewer system. This wastewater is carried to a wastewater treatment plant, where it goes through another multi-step cleaning process to remove pollutants before it is safely returned to a river or the ocean, rejoining the great water cycle once more. In a world where billions still struggle for access to safe water, the system that delivers it to our taps is a modern marvel. It's a silent, tireless servant, working 24 hours a day to protect our health and sustain our communities. And it's a testament to our ability, when we work together, to harness the power of nature for the good of all. For millennia, water has been a symbol of abundance. It has flowed from our rivers and fallen from our skies with what seemed like endless generosity. But as we drift into the 21st century, the story is changing. That sense of abundance is beginning to feel fragile. In many parts of the world, water is becoming a scarce and precious resource. Droughts are lasting longer. Floods are becoming more extreme. Glaciers are melting, and ancient aquifers are being depleted. This final chapter of our story is not about the distant past, but about our shared future. A future that will be defined by how we choose to value and manage every single drop. Let's begin with a dose of perspective. Our Earth is called the Blue Planet, and for good reason, but looks can be deceiving. Of all the water on Earth, over 97% is salt water in our oceans. Only about 5% is fresh water, and of that tiny fraction, almost 70% is locked away as ice in glaciers and polar ice caps. That leaves less than 1% of all the water on Earth easily accessible for us to use in our lakes, rivers, and groundwater. It is an astonishingly small sliver of the pie, and yet it must sustain over 8 billion people, countless ecosystems, and every facet of our modern world. Our demand for this limited resource is immense and growing. Agriculture is by far the biggest user, accounting for roughly 70% of all freshwater withdrawals globally. It takes a staggering amount of water to grow the food we eat. Industry comes next, using water for cooling, processing, and manufacturing. And finally, there is our domestic use, the water we drink, cook with, and use for sanitation. In many parts of the world, we are now using water faster than nature can replenish it. Groundwater aquifers that took thousands of years to fill are being pumped dry in a matter of decades. The Great Ogallala Aquifer, which lies beneath the American Great Plains and supports a huge portion of its agriculture, is being depleted at an alarming rate. Rivers like the Colorado in the American Southwest and the Indus in Asia are so over-allocated that they often run dry before they reach the sea. Layered on top of this growing demand is the profound impact of climate change. A warming world is scrambling the water cycle. Warmer temperatures mean more evaporation from soil and reservoirs, intensifying droughts. Mountain snowpack, which acts as a natural reservoir, is shrinking and melting earlier in the season, leading to water shortages in the summer. At the same time, a warmer atmosphere can hold more moisture, leading to more extreme rainfall events and catastrophic flooding. The water is still here, but it's showing up in the wrong places, at the wrong times, or in the wrong amounts. We are living in an age of water extremes. The challenges are daunting. But this is not a story of despair. It is a story of innovation and hope. Around the world, people are developing creative and inspiring solutions to our water crisis. One of the most promising is water recycling. Advanced treatment technologies can now purify wastewater to a level that is safe enough to drink. Cities like Singapore and Orange County, California, are pioneers in this field, turning what was once considered waste into a valuable new source of water. It's a closed-loop system that mimics nature's own cycle. Another key technology is desalination, the process of removing salt from seawater. While traditionally expensive and energy-intensive, new technologies are making it more efficient and affordable. For arid, coastal nations like Israel and Saudi Arabia, desalination is already a lifeline, providing a significant portion of their freshwater needs. But technology is only part of the solution. The other part is conservation. We can all do more with less. In agriculture, a shift from inefficient flood irrigation to precise drip irrigation can save enormous amounts of water. In our cities and homes, simple measures like fixing leaks, installing water-efficient appliances, and planting drought-tolerant landscapes can make a huge difference. Ultimately, the future of water will be shaped by a shift in our mindset. We must learn to see water not as an endless commodity to be exploited, but as a precious, finite resource to be cherished and shared. It requires a new water ethic, one that recognizes the deep connection between our own well-being and the health of the rivers, lakes, and aquifers that sustain us. It means making smarter choices in what we buy, what we eat, and how we live. Water has been our constant companion throughout our long journey on this planet. It was present at our birth and has flowed through every chapter of our history. It connects us to each other, to all other living things, and to the deep past. Now, it is asking something of us, to be wise stewards, to be thoughtful guardians, and to ensure that this eternal flow continues for all the generations to come. The future is not yet written, and the pen is in our hands. And so, we reach the end of our meandering journey. Though in truth, water's story has no end. It is a perfect circle, an eternal loop flowing from stardust to ocean, from cloud to river, from your own breath back into the great, shared atmosphere of our world. It is always moving, always changing, always returning. We have followed this humble molecule from the heart of distant stars to the bottom of primordial seas. We have watched it carve canyons, build civilizations, inspire myths, and challenge our ingenuity. And through it all, water has remained itself, simple in its form, miraculous in its function, and possessed of a quiet, relentless power. It is the silent author of our planet's story and the gentle current that runs through our own. As you settle deeper into your rest now, as your thoughts begin to soften and drift like mist on a calm lake, perhaps you will carry with you a new sense of wonder for this ordinary, extraordinary substance, for the cool glass on your nightstand, for the gentle sound of rain against the window pane, for the soft rhythm of your own breathing. Each is an echo of the great cycle that connects us all. Before we part ways for the night, I find myself returning to the question from our beginning. For the answers, like water itself, create a quiet connection across time and space. Where are you listening from tonight? What time is it in your part of the world? Are you cozy with a warm drink? Or are you simply letting the sound of this story be the gentle tide that carries you out to the deep ocean of sleep? If this journey has helped you to relax, if it has brought a measure of peace to your evening, I would be so grateful if you would leave a like or subscribe to this channel. Your quiet support helps me continue to chart these slow, soothing voyages for fellow dreamers like you. And with that, I wish you a deep and peaceful rest. May your dreams be clear and calm, like a still pool of water reflecting a sky full of stars. Good night.